Hello, welcome to my channel. Today we'll be talking about computer organization and architectures 2. This is my library assignment. Today I'll be talking about the design of the RISC-V Instruction Set Architecture. It is an open standard instruction set that began in 2010. It is based on the establishment of reduced instruction set computer. This is for my Comp Science 3833 class, so let's begin. So in this paper, I'll be talking about the hardware-software interface. It is embodied in the instruction set architecture, which is ISA. It is arguably the most important interface in the computer system. Yet, in contrast, to nearly all the other interfaces in a modern computer system, all of the commercially popular ISAs are proprietary. A free and open ISA standard has the potential to increase innovation in microprocessor design. It also reduces system cost, and as Moore's definition contains, it eased the transition to more specialized computational devices. As the RISC-V architecture, it is a load store architecture. Its floating point instructions use IEE 754 floating point number. So in the next slide, I'll be talking about the author. So the author is Andrew Waterman. He published this article in 2016. He is an electrical engineering and computer scientist. He studied at the University of California at Berkeley's. He is currently now working at S5, which is a semiconductor company to build customized silicon based on free and open RISC-V instruction set architecture. So he is working as a chief engineer that S5's products including cores, SOCS, IPS, and development boards. Here in the introduction, I'll be talking about how building the RISC-V, which stands for the Reduced Instruction Set Computer, it will be simple, budget-friendly, user-friendly, and energy efficient. So the innovation in computer system designs owe in no small part to a careful design of interfaces between subsystems. So in the next slide, I'll be talking about the design phase. So you may be wondering, why would we develop a new instruction set? So there are several commercial ISAs that are popular uses, and by reusing one of them, we would avoid the significant effort and cost of porting software to a new one. So the example of different instruction sets are like the popular commercial ISAs, which are proprietary. So the vendors have like the business selling implementation of their ISAs. So they do not welcome freely available implementations that might erode the profits. So they are quite difficult to fully implement in hardware, and yet there is little incentive to create a simple subset of ISAs without a complete implementation, also as an unmodified software which cannot run or compile, and undermining the justification of using an existing ISA. So even though we carefully considered the possibility of adopting an existing instruction set, Waterman wanted to build rather their own instruction set and developing their new instruction set. So, for example, here, as you can see in this table, it is a summary of several ISA support for the desirable architecture features. So, all of the architecture features lacks at least two important technical features. So, by looking at the table, given these limitations, we saw fit to develop their own instruction set. So, in creating the RISC-V, which means it is a free and open ISA which can avoid these technical features, pitfalls, and they can implement in many micro-architectural styles, which can help the design and the subject, which I'll be talking in the next few slides. So in implementations, they have included the goal of the RISC-V was to make a simpler ISA that is suitable for any computing device. So a feature of RISC-V should not over-architect any micropattern or implement fabric or have a specific target. So in creating the RISC-V, the challenges includes loading multiple or storing multiple instruction sets. The implementations can be quite difficult and depending which technical features the users are wanting to operate on. So what Waterman has done is they have technical goals in building their system into a smaller base ISA, which is free, open, and modular. And then it is also fixed, definitional, where the program is efficient in hardware support, and it is also fixed in missing its features and accepting multi-word atomicity. So in evaluation, the static compression of RVC code. The test was performed to measure the effectiveness of RVC and RISC-V by analyzing both static code size and the dynamic instruction from fetch traffic from each program versions. So on the right side of this slide, I have a table which is provided within the article. So in this figure, the frequency of the integer register usage in static code and the spec CPU 2006 benchmark suite. So the register is sorted by function in the standard RISC-V calling convention. So as you can see, several registers have special purposes in the ABI, which is time 0, which over here, so it is hardwired to a constant 0. So as the slide continues here, it will talk about how each of the static code size is in comparison of the dynamic fetch traffic of RSV and the RISC-V versions. So the dynamic compression of RVC code compared to RISC-V code in the spec of CPU 2006 benchmark suite. So as you can see, the dynamic savings from 35% down to 27%, which can adjust the compiler's cost model to penalize the use of non-RVC registers in code. So obviously, profiling data would improve this technique, since otherwise the static compiler must hazard a guess as to which code is likely to be frequently executed. So, in conclusion here, what I learned, the ISA-V base has different bases and extensions such as extension A all the way through extension F, E, C, and G. So there are um, atomic memory operations which can have a certain effect towards memory and its memory storage. So the system is free, public, and modular. Even though the architecture was complete, there still remains various works and interfaces towards the user ISA. So what I found out was how to implement different ideas and its different features which can benefit the ISA using development tools such as programming skills or using the table on the right. It can be calculated as the cumulative frequency of floating point registers usage in the spec CPU of 2006 benchmark suite, sorted in descending order of frequency. So the contributions are Waterman's team debated if they were including the load multiple and store multiple instruction set. So the code size and performance improvements of each new instruction set would create an extension for a new instruction width. So the compressing ratio of each RVC instruction are sorted by the performance balance between the implementation. So they compared other RISC-Vs like thumb and micro MIPs, which have been included in the instruction sets. So a study was performed to calculate how much impact a static code size and dynamic instruction count would be performed, which would be in this slide here. They calculated how each of the instruction set would have affect performance within each ISAs. So for for examples such as data movement from certain memory or registers of floating points, and along with a study of data figures of double precision float point used in algorithms and programming languages. So overall, my impression was the article was unique and interesting. Waterman provided information and fundamental concepts of creating an RISC-V instruction set or creating one from scratch. He included research, statistics, and abstract views of different instruction sets that have already been developed or can further be enhanced from the RISC-V instructions. I enjoyed I enjoyed looking at the different examples that he used, such as the graphs, the data figures, and charts that he used within the article. So Waterman provided graphs to create a comparison between the different ISAs and how he and his team can improve and create a ISA that is unique and different from programmers to create a user-friendly program for everybody to operate. So I guess that's all from my paper. Thank you.